We'll begin by looking at the iron meteorites. These are usually the easiest to identify, and they always contain a lot of iron. Most commonly 80% or more, 85%. Occasionally maybe down to 50, but that's pretty rare. They're black when they're fresh and haven't been on the ground long enough to rust, although that one from Argentina we see just on my right fell about 5,000 years ago, and most pieces are not rusted. Some are a little. The other three pieces are from a Russian fall in 1949 and just hasn't had a chance to rust. Now they have this black shiny surface, whereas inside they look like steel, nice and shiny, shiny metal. This black surface is called a fusion crust. It is the result of the freezing or solidification of the last little bit of melt that was forming on the surface of it as it came through the atmosphere. It's a mixture of iron from the meteorite and oxygen from the atmosphere. This is a famous piece all by itself. It's called the Hollinger meteorite, though it's really only the Hollinger fragment of the Canyon Diablo meteorite, an impact that created the crater in Arizona that I talked about in the first unit. There's been about 30 tons of this meteorite found altogether. This is the biggest piece at just a little over 600 kilograms, and there are around, well, more than 1,000 pieces, many of which are just small fragments. In this case, the fusion crust has weathered off a little bit. It's a very dry, arid climate, and you can see some of the exposed iron along the ridges, the edges of the regmaglyphs in this piece. Here's some other pieces of the Beringer crater meteorite, a Canyon Diablo meteorite, as it's usually called, after a little creek that runs not too far away from the crater. These three pieces are all to scale, so you can tell how big the biggest one is by looking at the little piece that's in, well, it's not my hand, in somebody's hand. So these are relatively small fragments, and you can see there's a little bit of rust on the middle one, and a little bit more rust on the one closer to me. There's another possible 30 tons of this meteorite still underground. These are bits that were left fell on the surface. Another 30 or so tons, uncertain of the weight. It penetrated the ground in the bottom of the crater. In drilling through the crater, they've hit some of these things, but they've never bothered to dig them out. Notice that every one of these pieces has a different shape to it. Highly angular is the usual case. So meteorites are not usually nice round spherical objects. They are highly irregular, stones included. Here's some more iron meteorites just to have a look at this shape business and also how they can change their appearance with rust. These are all about to the same scale. The one from China there, Chinga, it's a little bit over fist-sized. The Gibeon piece, there's a lot of that one fell in Namibia in East Africa, West Africa, sorry. And the Eurosa one in Brazil is quite badly weathered. It's so weathered that you can no longer see the regmaglyphs on it. It just rather rusted away. But it's inside the meteorite that really is the most interesting part. If you cut and polish an iron meteorite, they will look like those two on the top. Two different meteorites, one from Australia, one from Sweden, and you get this nice, shiny, metallic surface. In some cases, you can polish them up enough you could use them as a mirror. A lot of iron meteorites have other stuff in them, and two of the more common bits of stuff are bits of graphite, carbon, that you see in the picture on the left, or my left, and on the right you see a slightly bronzy looking three-dimensional, would be a sphere, more or less rounded shape. It's somewhat similar to earthly pyrite in that it's an iron sulfide, but it's not quite the same as pyrite. We call it troilite. So such nodules are fairly common in iron meteorites. In order to classify them, we have to take a closer look. Now we have two different kinds of classification that are totally different. The first one is based on what we see when we cut it, polish it, and then etch it with a chemical, or we'll try to etch it at least. Nitric acid can be used, but there are other chemicals that will do the etching. The other classification is based on fine details of the chemical composition, and I'll talk about it a little bit more momentarily. Well, there are three types of iron meteorites based on what we see when we cut, polish, and try to etch them. Octahedrites, the most common, the hexahedrites, next most common, and ataxites, number 3, almost rare. Only about, less than 5% of all the iron meteorites are ataxites, and about 75% or so are octahedrites. Now, these have all been etched. Notice that the ataxite has remained nice and shiny. The one right beside it, close to my right, is also an ataxite, but it has a bunch of small troilite nodules in it. The smallest one is about 1 millimeter in diameter. But they don't all have troilite. We don't really name them based on these kinds of inclusions. That becomes part of the description of an individual meteorite, but not part of the classification. All these ataxites that resist being corroded by acids are high nickel, nature's stainless steel. So ataxites have between about 16 and 20% nickel, what one can get from a chemical analysis. The octahedrites are next. They have maybe 6 to 18%, and the hexahedrites 4 to 7%, very little nickel. Most of them are over 5%. Well, the chemical classification of iron meteorites runs in parallel with these three structural groups. There are 15 chemical groups altogether, and this is based, it's not something you can see just looking at them. You have to do an extremely detailed chemical analysis. There's a group of elements we call trace elements. Gold is a trace element. There is some gold in some of these iron meteorites as well, and it plays a part in the classification, small part. But these trace elements, I won't bother saying a bunch of names, but if you happen to know, you might have heard the word gallium. That's one of them. Altogether, these make up a way less than 1% of the meteorite. Cannot be seen with the naked eye, nor even with a high-power microscope, but you can analyze for them with specialized equipment. So these 15 chemical groups all have different ratios of these variety of these different trace elements. Now, you cannot tell the structural grouping classification, nor can you tell the chemical grouping just by looking at the outside of the meteorite, and not even by looking at the inside, unless, of course, you polish it and etch it, and then you can get the structural group. But identifying the structural group tells you nothing about the chemical group. And likewise, determining this fine trace element chemistry tells you not very much about the structural groups either. So there are parallel classifications. We use them both for different purposes. Well, iron meteorites are the easiest to identify, and they're what most people think of when they hear the word meteorite. Yet, they're not the most common. They make up less than 5%, 4.5 to 4.7% of all known meteorites, whereas the stony meteorites make up 94%. The stony irons, about 1.5, maybe just slightly less. But iron meteorites on average are larger. They're still small ones, for sure, and I showed one of those earlier. It's a little wee tiny piece of this spring water sorry, wrong name, Whitecourt meteorite in Alberta. There are pieces smaller than this. I've got a dozen or so tinier. This is the biggest piece I found. But a piece about the size of my fist is about the biggest piece that's ever found for that one. Nonetheless, there are some huge pieces of iron meteorite weighing tons. The largest one is 67 tons. Next one's 34 tons. There's several 30-tonners, and there's a dozen or more that are over 10 tons. The stony meteorites, well, this is a smallish piece. They certainly get bigger, but there's nothing in the several ton range. A half a ton was produced by the Chelyabinsk event of 2013 in Russia, but most of the pieces from it were small, like this, and maybe up to fist-sized. So on average, they are much, much smaller. So the iron meteorites make up nearly 90% of all of the known meteorite mass, despite the fact that it's the stones that make up 94% of all the individual meteorites. And there are very few stone meteorites that are heavier than 30 kilograms.